So we've already seen how we model forces on objects, and we've drawn free body diagrams. We figured out how to calculate the acceleration of an object by looking at the forces, and sometimes we just want to determine the magnitude of some of the forces. Today, what we're doing is we're looking at what if there's a force on an object that's not directly straight up, not only straight down or to the right or to the left, but what if it's at some angle? We're pulling on this object at some angle. Newton's second law, we can pretty much only use it um, in one dimension at a time. And so our goal is to take this force and break it up into components. And so let's go ahead and try that. And if you have this set of notes, just cross out fx and fy. We're going to do it a little bit differently. First thing we'll do is we'll start with a free body diagram. And so this object, this box, actually it's a sled. It's being pulled across snow, so there's no friction. And it's being pulled with a force F1 at some angle. The angle is 30 degrees. F1 is 20 newtons of force, and the mass of the object is 8 kilograms. But let's draw the free body diagram for it. It has a gravitational force mg, and by now we should be thinking, doesn't everything have a gravitational force? Yes. And we will draw a normal force, Fn. And now we're going to, that's actually it. There's no friction on this, but what we're going to add is this last force, F1, and we'll do it here at some angle, 30 degrees, F1. So we've dealt with mg and Fn. We've never dealt with a force at an angle like this. Now, before we move on, what we're going to do is draw this again. This is the free body diagram, and this is correct. We want to leave that alone. I'm going to bring on here mg again. We're going to put on the normal force again. But what we want to do is break up F1, the F1 force, into components. And if you notice that F1 is going up and to the right, we're going to break it up into those components. We're going to have an upward one, and we're going to have a rightward component, right? Because it's kind of pulling it up and it's kind of pulling it off to the right. Now, in this case, this will be F1 sine theta, and this one will be F1 cosine theta. And I'm going to just go back a couple of lessons, hopefully not too far, to show you that we've done this before. Where is it? Where is it? Yeah, I'm sorry, we've done it right here. So we've broken up velocity vectors into components, a horizontal and a vertical. And I'm just pointing out here that horizontal would be cosine and vertical would be sine. In this class, that will pretty much always be true. Um, there are situations, though, where the vertical is not always sine, but for today and for this course, that will be the case. Cool. So why did we do that? We can't use F equals ma with this force F1 at this angle here. We can only use it with these components. So when you're pulling an object at an angle like this, you're kind of pulling it up a little bit and you're kind of pulling it to the right a little bit. Okay, so that's the meaning of those. So that's part C. Let's do part D, which is the acceleration. Now, it's given away in my picture here that the object is accelerating to the right. So we could have drawn an arrow here for acceleration, and we could have drawn an arrow here. If I want to determine the acceleration of this, I have to use Newton's second law. And remember back to our previous lesson, we're going to do this horizontally. In other words, the acceleration is horizontal, and so therefore when we substitute the forces, we only want the horizontal force in here. And so if you look at this one, don't look at this one, but at this one, the only horizontal force is F1 cosine theta equals ma. And we're trying to solve this for acceleration. So we'll divide both sides by m. And we can just substitute these numbers. F1 is 20 cosine of 30 degrees. And the mass is 8. So we can just type this right in the calculator. Make sure you are in degree mode. Pull up my calculator here, 20 cosine 30 over 8. I get 2.165. I'll say 2.17, whoops, meters per second squared. So that is the acceleration of the sled. Cool. Question E just wants to know what is the normal force on the box. And so we'll take F equals ma, and this is vertical. The normal force is on a vertical dimension. And here's what we're going to do. First of all, there's no acceleration vertically. So let's make that 0. M times 0 is 0, and so there we go. And I forget, we need a little bit of space here. Now we need the sum of all of the vertical forces. Now we have 3 of them. And here we get into a little issue with positive and negative. So let's take a look at this. I know that you guys know that if we put Fn first, we'll subtract mg. But what do we do with F1 sine theta? Do we add it or subtract it? And I use the analogy of like a tug of war. When two people are pulling in the same direction, we should add those forces together. And so that's what we'll do here. We'll say Fn plus F1 sine theta minus mg. Looks good to me. We want to solve for Fn. And so that means we're going to have to add mg over to the other side. Let's fix that. And while we're at it, why don't we subtract F1 sine theta, because we need to isolate Fn. And that cancels. So this will say Fn equals mg minus F1 sine theta. So Fn equals, gosh, what was the mass of this thing? 8. So that's 80 minus 20 sine of 30 degrees. 80 minus 20 sine 30 degrees. Oh, I get an answer of 70. Newtons. Cool, let's take a look at this. Notice how the gravitational force is 80 newtons, because it's 8 times 10, but Fn is only 70 newtons. When you pull up on an object a little bit, we are essentially decreasing the amount of normal force on the object. We're decreasing the amount that the floor is having to push back on the object. That kind of makes intuitive sense. Cool, that's one example. I believe the second example, oh, also doesn't have friction. Okay, well, that's good. But the difference here is that this object is getting pushed down and to the right. We're pushing down on it, but also kind of pushing it to the right. It will accelerate to the right. It's a lawnmower. Now again, we're going to get rid of A and B, which, by the way, let's go back here. This is what I used to call fx, and this is what I used to call fy, just so you know. So let's draw a free body diagram for this one. Here is the box, or I'm sorry, the lawnmower. Gravitational force, mg. Now the ground is pushing back up on it with a normal force Fn. And let's not forget about this F1 force. Whoops. Oh, of course we are not going to use that one. Gosh, I'm trying to, this thing is real slippery, so you'll have to excuse me. Okay, let's not do anything fancy. There we go. Now, if we're pushing down on the object and to the right, pushing down and to the right, we're going to have two components for F1. I just cannot seem to get these things straight. So we have a downward and we have a rightward force, or component, I should say. Now, let's see here. Nothing different here. The horizontal one will be cosine, and the vertical one will be sine. Let's not forget about Fn, though. Still goes here, and mg still goes here. Supposed to be straight downward. Cool. The one on the left is the free body diagram, but the one on the right is the one we will use. Let's determine the acceleration of the box, or the lawnmower. And so if we know it's accelerating to the right, we will say we're going to analyze the horizontal Newton's second law. Horizontally, there is just F1 cosine of theta equals ma. We'll divide by m to solve for a. And so we'll plug in some numbers. It's 10 cosine of 40. The mass is 15. So I'll get my calculator. Using my phone, which is not a good calculator to use. 10 cosine 40. Let me make sure I'm not making any mistakes here. I get 0.51 for the acceleration. Cool. And then we have part E. What is the normal force? Okay. So of course we're going to do vertical. The lawnmower should not be accelerating vertically, just horizontally. So F equals ma. A is 0. And the tricky part with the vertical is putting in these vertical forces slash component into this equation here. I'm going to put Fn first. And notice that both mg, we're going to subtract mg, but notice that F1 sine theta is also opposite of Fn, so we have to subtract F1 sine theta. You might say, aren't these two forces added together. So shouldn't it be mg plus f1 sine theta? And you're absolutely right. If we're going to do it that way, though, we should put it in parentheses because it will be the normal force Fn minus the combined forces here. But if you know about your distribution, that negative gets distributed, and so we have this here. Let's get Fn by itself, and so we're going to have to add mg to both sides. We're going to have to add f1 sine theta to both sides. And so we have Fn equals mg plus f1 sine theta. And at this point, we're just going to plug in some numbers. The mass is 15. So mg is 150 plus, looks like it's 10 sine 40. And I'm getting a normal force of 156. Let's see. You may notice that mg is 150 and Fn is 156. And that's because we're pushing down on the lawnmower some with this F1 sine force component. And so if the if the lawnmower is pushing down on the ground a little bit more, then the ground must push back an equal amount. So there's still no acceleration vertically, it's just that the normal force is greater than mg by itself. But it is equal to mg plus F1 sine theta. That's it, that's forces with angles.